Hey, you all. Did you know that when you lie still in bed at night, just breathing, not moving, you are, in fact, falling? Not down toward the floor, not sideways, but falling through time, along a curve in the very fabric of reality itself. A curve that has been shaped by every star, every galaxy, every bit of mass and energy that has ever existed. You are not sitting still in space. You are gliding ever so gently along a path that was carved out billions of years ago, and that path is not straight. It is bent. It is warped. It is curved. And whether that curve ever closes back on itself, whether the universe loops around like the surface of a sphere or stretches on forever like an endless flat plane, is one of the deepest questions we can ask. Tonight, we're going to explore that question together. Is the universe infinite? Not just big, not just unimaginably huge, but truly, mathematically, physically infinite. And to get there, we won't start with telescopes or equations. We'll start with something familiar, a trampoline. Imagine you have a trampoline in your backyard, one of those round ones with a tight, stretchy fabric surface. Now take a heavy bowling ball, something dense, substantial, and place it gently in the center. What happens? The fabric dips. It curves downward. A depression forms around the ball. That's not just a metaphor. That's a real physical analogy, a surprisingly good one for how gravity works in our universe. But here, where it gets strange. In the trampoline, the fabric dips into a third dimension down into the space beneath the trampoline. But in our universe, in real space-time, there is no beneath. There is no outside. The curvature we're talking about doesn't require extra dimensions to bend into. It is intrinsic. That word intrinsic is important. It means the curvature is a property of the space itself, detectable from within it without needing to peek from the outside. You don't need to leave the universe to measure whether it's curved. You can do it just by walking, or rather, by sending light and seeing how paths behave. How? Well, imagine you're a two-dimensional creature living on the surface of that trampoline, a flatlander if you will. You cannot move up or down. You only know forward, backward, left, and right, but only along the surface. If the trampoline is flat and empty, and you draw a triangle by walking 3 straight lines, say, 10 steps east, 10 steps north, then back to start, your angles will add up to exactly 180 degrees. That's Euclid's rule. The angles in a triangle sum to 180 degrees in flat space. Now place the bowling ball on the trampoline. The surface curves. You, as the flatlander, still can't see the dip. You have no concept of down, but you can notice something odd. You walk your triangle again, 10 steps along what feels like a straight line, the shortest possible path on the surface, then turn, walk another 10, turn again, walk back. But now, when you measure the angles, maybe using a tiny protractor you carry in your flatlander pocket, you find they add up to more than 180 degrees. Maybe 185, maybe 190. The bigger the dip, the stronger the curvature, the larger the sum. Conversely, if you were on the surface of a saddle, a shape that curves upward in one direction and downward in the other, your triangle's angles would add up to less than 180 degrees, 175, 170. That kind of curvature is called negative curvature. So here's the key idea. Curvature isn't about bending into some higher space. It's about how geometry changes internally. In flat space, zero curvature, parallel lines stay parallel forever. Triangles have 180 degrees, and the circumference of a circle is exactly 2 times pi times the radius. But in curved space, all of those rules break, not because math is wrong, but because space itself is different. And this internal measurable deviation from Euclidean geometry is what Einstein realized gravity is. Gravity is not a force that pulls across space like magnetism. Gravity is the curvature of spacetime itself. And objects, planets, light beams, you in your bed, simply follow the straightest possible path through that curved geometry. Those paths are called geodesics. A geodesic is the equivalent of a straight line on a curved surface, like the great circles on a globe, the equator or lines of longitude. On Earth, if you fly from New York to Tokyo along the shortest path, You don't go straight east on a flat map. You curve northward over Alaska. That looks curved on paper, but on the sphere, it's the straightest possible route. So in the universe, planets orbit stars not because a force is tugging them inward, but because they're moving straight ahead in four-dimensional spacetime, along a geodesic that's been bent into a loop by the star's mass. The sun doesn't reach out and grab the Earth. The sun tells spacetime how to curve, and spacetime tells the Earth how to move. Now, here's a formula that captures part of this, not the full complexity, but the core idea from Einstein's field equations. In words, the curvature of spacetime at a point equals a constant, called 8 pi times the gravitational constant, divided by the speed of light to the fourth power, multiplied by the energy and momentum present at that point. Let me say that again, slowly. The amount and type of curvature of spacetime is directly proportional to the density and flow of mass and energy right there, plus a little extra term Einstein later added, called the cosmological constant, which acts like a baseline energy of empty space. But for our purposes tonight, thinking about the entire universe, we don't need the full, messy, point-by-point version of that equation. We can use a simplified model, the Friedmann-Lemaitre-Robertson-Walker metric, or FLRW for short. Don't worry about the name. What it gives us is a description of a universe that is, on large scales, the same everywhere, homogeneous, and looks the same in every direction, isotropic. That's the cosmological principle, and all our observations, from the cosmic microwave background to galaxy surveys, support it, at least when we zoom out far enough. The FLRW model describes the universe's shape using just one number, the curvature constant, often labeled k, and this k can take only 3 possible values, +1, 0, or -1. Each corresponds to a different global geometry. If k equals +1, the universe has positive curvature, like the surface of a sphere, but in 3 dimensions. We call this a closed universe. It has finite volume, no boundaries, just like how you can walk forever on Earth's surface without falling off. And if you went far enough in one direction, you'd eventually return to where you started. If k equals 0, the universe is flat, Euclidean. Parallel lines stay parallel. Triangle angles sum to 180. It could be infinite in extent, stretching forever in all directions. Or it could be finite but with a more complex topology like a torus, a 3-dimensional donut shape, where space wraps around on itself. We'll come back to topology soon. If k equals -1, the universe has negative curvature like a saddle or a Pringle chip, extended in all directions. This is an open universe. It has infinite volume, and triangles have angle sums less than 180 degrees. So the question, is the universe infinite? Hinges on 2 things, its curvature and its topology. Curvature tells us about local geometry, how space bends from point to point. Topology tells us about global connectedness, how the whole thing is stitched together. You can have flat geometry but finite size if, for example, space is shaped like a video game screen. Walk off the right edge, reappear on the left. That's a toroidal topology. The geometry is flat, rulers and protractors behave normally, but the universe is finite and without edges. So let's unpack curvature first, because that's what we can actually measure. How do we measure the curvature of the entire universe? We can't step outside and look, but we can do what the Flatlander did, use triangles. Only our triangle is made of light. Here, how it works. Shortly after the Big Bang, about 380,000 years in, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. Before that, the universe was a hot, dense, opaque fog of plasma like the inside of the sun, where photons couldn't travel freely. They kept scattering off charged particles. But once atoms formed, the fog lifted. Photons were set free. That flash of light, stretched by cosmic expansion into microwaves, is what we detect today as the cosmic microwave background, or CMB. The CMB is like a baby photo of the universe. a snapshot of what space looked like when it was only 380,000 years old. And across that sky, we see tiny temperature variations, ripples, about 1 part in 100,000. These ripples come from sound waves that traveled through the primordial plasma, regions of slightly higher and lower density, like waves in an ocean. Now here's the beautiful part. We know the actual physical size of those sound waves. Physics tells us that in the hot, early universe, the maximum distance a sound wave could travel before recombination, before the fog lifted, was about 490,000 light-years. That distance is called the sound horizon, the radius of the largest possible ripple. So imagine, at the moment the CMB was emitted, there were many spherical ripples of hot and cold gas, each with a known radius, 490,000 light-years, scattered across space. When we look at the CMB today, we see the angular size of those ripples on the sky, how many degrees wide they appear. And that angular size tells us the geometry of space, just like holding a ruler at arm's length. If the ruler looks small, it's far away. If it looks large, it's close. But in curved space, the same physical size can appear larger or smaller than expected. In a flat universe, zero curvature, a ripple with a physical diameter of 490,000 light-years, located at the distance of the CMB, about 46 billion light-years away, due to expansion, should appear to be about 1 degree across on the sky. Just 1 degree, about twice the width of the full moon. In a positively curved, closed universe, light rays converge as they travel. Think of two people walking north from the equator. Even if they start parallel, they meet at the North Pole. In the same way, light from opposite sides of a ripple is bent inward by positive curvature, so the ripple appears larger on the sky than it would in flat space. Maybe 1.5 degrees, maybe 2. In a negatively curved, open universe, light rays diverge. Parallel paths spread apart, so the same ripple appears smaller, maybe only 0.7 degrees across. So what do we see? Observations from satellites like WMAP and more precisely, Planck, which map the CMB with incredible accuracy, show that the most prominent ripples, the first acoustic peak, are almost exactly 1 degree across. The measured angular scale is 0.8 degrees, but when you account for the expansion history of the universe, the inferred spatial curvature is consistent with 0. In fact, the Planck data constrain the curvature parameter, often written as omega k, to be between -0.011 and +0.008 at 95% confidence. That means if the universe is curved, the radius of curvature is at least 20 times larger than the observable universe, which is about 93 billion light-years across. So even if it's not perfectly flat, it's so close to flat that for all practical purposes, and for all philosophical purposes, too, it might as well be. But here's the catch. Measuring curvature to be 0 does not tell us whether the universe is infinite, because remember, topology is separate. A flat universe can be infinite, like an endless grid, or finite, like a torus, or even more exotic shapes. A Klein bottle, a dodecahedral space, a twisted cube. So now we come to topology, the study of how space is connected globally. Topology doesn't care about distances or angles. It cares about continuity, holes, and loops. Stretch a coffee cup into a donut in topology, they're the same, because both have one hole. Squish a sphere into a cube, still the same, no holes. So what topologies are possible for our universe? Well, if curvature is positive, k equals +1, the only simply connected possibility is the three-sphere, the set of all points equidistant from a center in four-dimensional space. It's finite, has no boundary, and every loop can be shrunk to a point. But there are also multiply connected versions like projective space, where going halfway around the sphere brings you back flipped, like a Möbius strip but in 3D. If curvature is negative, k equals -1, there are infinitely many possible topologies, most of them finite, some infinite with intricate fractal-like structures. These are called hyperbolic manifolds. They're mathematically rich but observationally elusive. But since observations strongly favor flatness, k equals 0, let's focus there. In flat, three-dimensional space, the simply connected, infinite version is just ordinary Euclidean space, infinite in all directions. But the finite flat possibilities are the compact flat manifolds. There are exactly 17 in 3 dimensions, but only 10 are orientable, meaning you don't come back mirrored. The simplest is the 3 torus. Take a cube and glue the left face to the right face, the front to the back, and the top to the bottom. Walk off one side, reappear on the opposite. No edges, finite volume, flat geometry. You could, in principle, see the back of your own head if the universe were small enough and light had time to loop around. So, could our universe be a giant 3 torus? We can test that. If space wraps around, then the CMB should show matching circles, pairs of circles on opposite sides of the sky that have identical temperature patterns, because they're actually the same physical region, seen from 2 directions, like seeing the same wallpaper pattern repeat on connected walls. Astronomers have searched for these matching circles. The Planck team did an exhaustive analysis. They found no statistically significant pairs. That means if the universe is toroidal, the repeating length, the size of the cube before gluing, must be larger than the diameter of the observable universe. In other words, even if space is finite and wraps around, we can't see the wrap, not because it doesn't exist, but because light hasn't had time to circumnavigate it in 13.8 billion years. The current lower limit on the size of a toroidal universe is about 98.5% of the diameter of the observable universe, meaning the fundamental domain, the smallest repeating unit, must be at least about 91 billion light-years across. So again, even if finite, it's effectively infinite from our perspective. And this is important, there are other topologies that don't produce matching circles. Some twisted shapes like the half-turn space or the quarter-turn space, where when you glue the faces, you also rotate them. In those cases, the matching patterns are more subtle, not circles, but correlated hot and cold spots in specific orientations. Those are harder to rule out, but so far, no evidence has been found. So where does that leave us? Observationally, the universe is flat to within a fraction of a percent, and if it has a non-trivial topology, it's on a scale larger than we can observe. That means the observable universe, the part we can see, is finite, a sphere about 93 billion light-years in diameter, centered on us. But the entire universe, that could be vastly larger or truly infinite. Now let's pause for a moment because there's a deeper layer here. When physicists and cosmologists say the universe is flat, they usually mean the spatial curvature at a fixed cosmic time, like slicing spacetime into moments like pages in a book, and asking whether each page is flat. But spacetime itself, the full 4-dimensional thing, is definitely curved. How do we know? Because the universe is expanding. Expansion is curvature in time. Imagine a grid of galaxies, not moving through space, but carried apart as space itself stretches. The distance between any 2 galaxies increases over time, not because they're flying apart, but because the metric, the ruler we use to measure distance, is changing. That time-dependent stretching is encoded in the scale factor, usually called A of t, and the way A of t changes, whether it's accelerating, decelerating, or coasting, tells us about the curvature of spacetime. The evolution of the scale factor is governed by the Friedmann equations, 2 key equations derived from Einstein's field equations, under the assumption of homogeneity and isotropy. The first Friedmann equation, in words, says, the square of the rate of change of the scale factor divided by the square of the scale factor, that's the square of the Hubble parameter, which measures how fast the universe is expanding right now, equals 8 pi times the gravitational constant, times the total energy density, including matter, radiation, and dark energy, divided by 3, minus the curvature constant k times the speed of light squared, divided by the square of the scale factor, plus the cosmological constant times the speed of light squared, divided by 3. Let me say that again more slowly. The expansion rate squared is proportional to how much stuff is in the universe, minus a term that depends on spatial curvature, plus a term from dark energy. This equation tells us that curvature fights against expansion and matter. If K is positive, closed universe, that minus K term is negative, so it reduces the expansion rate. If K is negative, open, it adds to the expansion rate. If K is 0, flat, that term vanishes. But here, the surprise. In the early universe, radiation and matter dominated, and their densities diluted as the universe expanded, matter like 1 over scale factor cubed, radiation like 1 over scale factor to the 4th. Meanwhile, spatial curvature diluted like 1 over scale factor squared, faster than matter, slower than radiation. So in the very early universe, curvature was negligible unless it was enormous. But as expansion continued, curvature would grow relative to matter, unless it was exactly 0. Yet we see it's still nearly 0 today, after 13.8 billion years of evolution. That's the flatness problem, one of the motivations for cosmic inflation. Inflation proposes that very early on, around 10 to the minus 36 seconds after the Big Bang, the universe underwent a phase of exponential expansion, driven by a field called the inflaton. During that time, the scale factor grew by a factor of at least 10 to the 26, possibly much more. An exponential expansion acts like a cosmic iron. It flattens out any initial curvature, just as inflating a balloon makes its surface look flatter and flatter to a tiny ant on it. So if inflation happened, and most cosmologists think it did, because it also solves the horizon problem and predicts the correct spectrum of CMB fluctuations, then it's no surprise the universe looks flat today. In fact, it would be astonishing if we measured significant curvature that would challenge inflation itself. But inflation doesn't tell us whether the universe is finite or infinite. Some inflationary models produce a single, connected universe, possibly infinite. Others produce a multiverse, a vast ensemble of pocket universes, each with different properties, embedded in an ever-expanding, inflating background. In that picture, our universe, the part that inflated from one region, could be finite or infinite, depending on the details. And here, another twist. Even if the classical geometry is flat and infinite, quantum gravity might change the story at the smallest scales. We don't yet have a complete theory of quantum gravity, string theory, loop quantum gravity, causal sets. They're all works in progress. But many suggest that spacetime might not be smooth and continuous all the way down. It might be discrete, made of tiny atoms of space, or emergent, like temperature emerging from atomic motion. If spacetime is emergent, then asking whether the universe is infinite might be like asking whether the ocean is infinite, when really it's made of molecules, and the concept of ocean only makes sense above a certain scale. Infinity might not be a fundamental property, just an approximation that works well at large distances. But let's return to what we can say, based on what we've measured. We know the universe is expanding. We know that expansion is accelerating, discovered in the late 1990s by observing distant supernovae. That acceleration is attributed to dark energy, a smooth, persistent energy inherent to space itself. In Einstein's equations, it's modeled by the cosmological constant, a number that doesn't dilute as space grows. Now, if dark energy is truly constant, if it's the cosmological constant and nothing more, then the future of the universe is clear. Expansion will continue forever, accelerating, stretching space so much that distant galaxies will eventually vanish beyond our cosmic horizon. The observable universe will shrink not in size, but in content, as light from farther regions can no longer reach us. In that scenario, even if the whole universe is infinite, we will only ever have access to a finite patch, a cosmic island, surrounded by an ever-growing void. And in the far, far future, trillions of years from now, all other galaxies will have disappeared from view. Civilizations arising then would see only their own local group, and might conclude they live in a static, eternal island universe, completely unaware of the vastness that once was. But that's only if dark energy is constant. What if it's not? What if it's a dynamic field called quintessence that could weaken or even become negative? If dark energy decays, expansion could slow, stop, and reverse, leading to a big crunch. In that case, a closed universe would recollapse, but even a flat or open one could if dark energy turns repulsive to attractive. Alternatively, if dark energy grows stronger over time, a scenario called phantom energy, expansion could accelerate so violently that it rips apart galaxies, stars, planets, and finally atoms themselves, the Big Rip. But current data from supernovae, baryon acoustic oscillations, and the CMB all favor a cosmological constant. The equation of state parameter W, defined as pressure divided by energy density, is measured to be minus 1.03 plus or minus 0.03. And minus 1 is exactly what the cosmological constant predicts. So again, observationally, we're led to a flat, ever-expanding universe, dominated by dark energy, with no sign of global topology on observable scales. But let's go deeper into what infinite really means. In mathematics, infinity isn't a number. It's a concept, and there are different sizes of infinity. The set of whole numbers 1, 2, 3, and so on is infinite, but it's countably infinite. The set of real numbers, all the points on a line, is uncountably infinite, a larger infinity. If the universe is infinite in extent and roughly uniform, as the cosmological principle suggests, then something extraordinary follows. Every possible finite configuration of matter must repeat infinitely many times. Why? Because in an infinite space with finite possible states per volume, due to quantum mechanics, there are only so many ways particles can be arranged in, say, a cubic meter. Then by the pigeonhole principle, patterns must recur. So somewhere unimaginably far away, not in another universe, but in this one, there is another Earth, another you, reading this script or not. Maybe one where you paused the video. Maybe one where you decided to make a cup of tea instead. The number of variations is finite. The space is infinite. So all possibilities are realized not once, not twice, but infinitely often. This is not science fiction. It's a direct consequence of infinity plus uniformity plus quantum discreteness. It's called the cosmological multiverse, or level 1 multiverse, in Max Tegmark's classification. And this is crucial, we can never observe those other regions. They lie beyond our particle horizon, the maximum distance light could have traveled since the Big Bang. Even if the universe is infinite, we are causally isolated from almost all of it. Our observable universe is a finite bubble in a possibly infinite ocean, and the ocean's waves will never reach our shore. So for all practical purposes, for physics, for astronomy, for human experience, the universe is finite. Not because it necessarily ends, but because we can never interact with more than a finite part of it. And that brings us to philosophy. What does it mean for something to exist if it's forever beyond observation, beyond influence, beyond any possible signal? Some physicists, like George Ellis, argue that only the observable universe is scientifically meaningful. The rest is metaphysics. Others, like Sean Carroll, say that the equations of general relativity naturally describe a global spacetime, and if the simplest models that fit the data are infinite, we should take that seriously, even if we can't see it all. There's no consensus, and there may never be because by definition, we can't gather evidence from beyond our horizon. But here, a thought experiment to help feel the difference between flat and curved, finite and infinite, one you can do lying in bed. Imagine you're floating in deep space, no stars, no galaxies, just you and a flashlight. You turn it on. The beam travels straight, or does it? In flat space, yes, it goes on forever in a straight line, getting dimmer but never bending. In positively curved space, a closed universe, the beam curves around and, after a very long time, comes back to you from behind. You could, in theory, see the back of your own head, illuminated by your own flashlight, after light has circumnavigated the cosmos. In negatively curved space, the beam diverges, parallel rays spread apart. So two flashlights pointed in nearly the same direction would gradually drift farther and farther apart. Now replace the flashlight with the CMB. We see the CMB coming from all directions, a spherical shell at the edge of our observable universe. If the universe were small and closed, we would see multiple images of the same CMB features, like seeing the same star in multiple places in a hall of mirrors. But we don't. The CMB is unique in every direction, no repeating patterns, no matched circles, at least, none we can detect. So the universe, if curved, must have a radius of curvature much larger than 46 billion light-years. And if flat, it could still be finite, but again, larger than we can see. One more idea. Cosmic topology could leave imprints not just in the CMB, but in the distribution of galaxies. If space wraps around, then galaxy clusters might appear in multiple locations, like seeing the same tree through different windows of a mirrored room. Surveys like the Sloan Digital Sky Survey have searched for such repeating patterns, looking for ghost clusters, and found none. Again, if the universe repeats, the repeat scale is larger than about 1 billion parsecs, about 3.26 billion light-years. But even that limit is much smaller than the full observable radius, so the door remains open, just barely. Let's now revisit Einstein and the meaning of straight. In special relativity, before gravity, spacetime is flat. It's called Minkowski space, named after Hermann Minkowski, Einstein's former math professor, who showed that space and time must be unified. In Minkowski space, the distance between two events isn't just space squared plus time squared. It's space squared minus time squared, times the speed of light squared. That minus sign is crucial. It's what makes time different from space and allows for light cones, causality, and the speed of light as a limit. The spacetime interval s squared equals the speed of light squared times the time difference squared, minus the space difference squared. If s squared is positive, the events are time-like separated. You could travel between them at less than light speed. If s squared is 0, they're light-like, only light can connect them. If s squared is negative, they're space-like, no signal can pass between them. They're outside each other's light cones. Now when gravity enters, spacetime is no longer Minkowski, but locally at any single point it is. That's the equivalence principle. In a small enough free-falling lab like the International Space Station, you can't tell whether you're in orbit around Earth or floating in deep space. Gravity disappears locally. Spacetime looks flat. You can set up a local Minkowski coordinate system, and in that patch, special relativity holds. But as you move from patch to patch, as you compare distant regions, the curvature shows up. The local flatness doesn't add up to global flatness. Just like how a soccer ball is made of flat hexagons and pentagons, but the whole thing is round. And that's how we define curvature mathematically, using parallel transport. Imagine you're at the North Pole holding an arrow pointing south, say, toward Greenwich, England. You walk straight down to the equator, keeping the arrow pointed in the same direction relative to your path, not turning it, just moving it forward. When you reach the equator, the arrow is still pointing south, along the line of longitude. Now you walk east along the equator, 90 degrees, to India. You keep the arrow pointing in the same direction, which now means it's pointing perpendicular to your path, because you're moving east, and the arrow is still aligned with the meridian you came down. Then you walk north, back to the North Pole along the new longitude. When you arrive, the arrow is no longer pointing toward Greenwich. It's pointing 90 degrees to the east toward India. Even though you never rotated the arrow, you just carried it straight, it came back rotated. That's holonomy, and it's a direct measure of curvature. In flat space, parallel transport around any loop brings the arrow back unchanged. In curved space, it doesn't. The amount of rotation is proportional to the curvature enclosed by the loop. We can do this with light or with gyroscopes. The Gravity Probe B satellite, launched in 2005, carried ultra-precise gyroscopes in polar orbit around Earth. Over time, the spin axes drifted not due to friction, but due to two effects predicted by general relativity: the geodetic effect from space curvature around Earth and frame dragging from Earth's rotation dragging spacetime around with it. The results matched Einstein's predictions to within 0.28%. So we've measured spacetime curvature right here, in Earth's backyard. But again, that's local curvature. The question of global curvature of the universe as a whole is different. And here's something subtle. The curvature we measure in the Friedmann equation is spatial curvature on a slice of constant cosmic time. But cosmic time itself is a choice, a convention. In an inhomogeneous universe, full of galaxies and voids, there's no unique way to slice spacetime into now surfaces. So the notion of the curvature of the universe is only well-defined because the universe is so smooth on large scales. If the universe were lumpy all the way up, no averaging possible, we couldn't even define a global curvature. But thanks to inflation and the physics of the early universe, the lumpiness is small, only about 1 part in 100,000 in the cmb, and grows slowly over time via gravity. So the FLRW model is an excellent approximation. Now let's talk about boundaries, or rather the lack of them. People often imagine the universe expanding into something like a balloon inflating into a room, but that's misleading. The balloon analogy is useful for curvature. The surface is two-dimensional, curved, finite, no edge, but the room is not part of the universe. In reality, there is no outside. The universe isn't expanding into space. It is space and time coming into being. Think of it this way. Every point in space is moving away from every other point, not because they're flying apart, but because the metric, the rule for measuring distance, is stretching. There is no center, no edge. Like raisins in rising bread dough, every raisin sees every other raisin receding, and the farther away a raisin is, the faster it appears to move, Hubble's law. So if the universe is finite and closed like a three-sphere, it has no boundary. You can travel forever and never hit a wall. If it's infinite and flat, same thing. The only way to have a boundary is to impose one, and no known law of physics requires or suggests a boundary. In fact, boundaries raise difficult questions. What's on the other side? What happens to fields and particles at the edge? General relativity works best on manifolds without boundary. So whether finite or infinite, the universe likely has no edge, only horizons. And horizons are not walls. They're limits of knowledge. Our particle horizon is the farthest we can see, set by the age of the universe and the speed of light. Our event horizon, in an accelerating universe, is the farthest we will ever see. Galaxies beyond a certain distance are receding so fast that their future light will never reach us. Right now, the cosmic event horizon is about 16 billion light-years away. That means galaxies farther than that are already lost to us, not because they're gone, but because space between us is stretching faster than light can cross it. Note, nothing moves through space faster than light, but space itself can expand at any rate. So even if the universe is infinite, our future is finite in terms of what we can observe. And in the far future, as expansion accelerates, even the Milky Way and Andromeda, which will merge into one galaxy, Milkomeda, will be alone in the dark. But that's billions of years away. Let's return to the original question. Is the universe infinite? After all this, after curvature, topology, inflation, dark energy, what can we say? We can say this: Based on the best measurements we have from the Planck satellite, from baryon acoustic oscillations, from supernovae, the universe is spatially flat to within a fraction of a percent. That means if it's curved, the radius of curvature is at least 500 billion light years, over 5 times the radius of the observable universe. We can say that if the universe has a simple topology, like a torus, it must be larger than the observable universe, or else we would have seen repeating patterns in the CMB or galaxy surveys. We can say that inflation, our best theory for the universe's first moments, naturally produces a universe that is extremely flat and possibly infinite. Earlier, we spoke about the 3 torus, the cosmic donut, where space wraps around on itself in all 3 directions. But that's only one of many possible finite, flat shapes. Let's walk through a few more, not to memorize names, but to feel the variety of ways space could be connected, like learning the shapes of rooms in a vast, invisible mansion. Imagine again a cube of space. In the simple 3 torus, you glue opposite faces directly, left to right, front to back, top to bottom, no twist, no turn, straight forward. Now consider the half-turn space. Here, when you glue the left face to the right face, you rotate it by 180 degrees before attaching. So if you walk out the right side of the cube, you don't just reappear on the left, you come back upside down and backward. Your left hand is now where your right hand was. But because the rotation is 180 degrees, a full half-turn, the space remains orientable. You don't become your mirror image. You're still you, just rotated. Then there's the quarter-turn space. Glue left to right with a 90-degree rotation. Now, every time you loop around that axis, you spin a quarter turn. After 4 loops, you're back to your original orientation. This space still has flat geometry. Rulers and lasers behave normally inside any small region, but globally, directions get subtly scrambled. Even more exotic is the Hansch, went manifold, one of the 10 orientable compact flat spaces. It's built by gluing faces with combinations of flips and half-turns in different directions. In this shape, there are no non-contractible loops that preserve orientation in a simple way. Every loop that goes around twists you somehow. Yet again, flat, finite, no edges. Why does this matter? Because if our universe had any of these topologies, and if the cube were small enough, we would see ghost images of galaxies, repeated patterns in the cosmic microwave background, or correlated fluctuations in specific geometric arrangements. Astronomers have searched for these signatures using statistical tools called correlation functions and matched circle tests, scanning the sky for pairs of points that know about each other not by proximity, but by topology. And so far, no signal, not a whisper. The universe, on the largest scales we can probe, is simply connected, or if it's multiply connected, the fundamental domain is larger than about 90 billion light years across. But here's something fascinating. Even if the topology is trivial, even if space is just an infinite grid, causality makes it effectively finite for any observer. Because of the finite speed of light and the finite age of the universe, no one, not you, not an alien in a distant galaxy, not a supercomputer in the year 10 to the 100, can ever gather information from more than a finite volume. That volume is our causal patch, the set of all events that could have influenced us, or that we could influence. Think of it like this. At the moment of the Big Bang, or more precisely, at the end of inflation, quantum fluctuations were stretched to cosmic scales. Those fluctuations seeded all the structure we see: galaxies, clusters, voids. But only the fluctuations within our causal patch became the galaxies we see. Fluctuations beyond our horizon evolved independently. They belong to other causal patches, possibly with different densities, different arrangements, maybe even different physical constants, if the multiverse idea holds. So even in a single, infinite universe, reality fractures into isolated islands of experience, each with its own observable cosmos, its own arrow of time, its own story. You are not just in the universe, you are the center of your universe, not by privilege, but by physics. Every observer everywhere has their own spherical horizon, their own bubble of knowable reality. That might sound lonely, but it's also humbling. It means no one has the whole picture. Not ever. Science, then, isn't about capturing the final truth of everything. It's about mapping, as faithfully as we can, the island we're on and learning to read the faint signals that wash up on our shores from beyond. Now, let's step back in time, centuries back, to see how our understanding of infinity has evolved. For most of human history, the universe was thought to be finite and Earth-centered. Aristotle in ancient Greece argued that the cosmos must be bounded because infinity, he claimed, could not exist in reality. It was only a mathematical abstraction. Beyond the outermost sphere of fixed stars, he posited, there was nothing, no space, no time, no outside. The universe was a perfect, finite, crystalline structure, and it made sense. After all, you can't walk forever. You hit the sea, the mountains, the edge of the known world. That view held for nearly 2,000 years, until the Copernican revolution. Copernicus moved Earth from the center, but still kept the universe finite, now with the sun at the hub, surrounded by planetary spheres and an outer stellar shell. Then came Giordano Bruno, a Dominican friar, philosopher, and visionary who dared to imagine more. In the late 1500s, he proposed that the stars were distant suns, each possibly surrounded by its own planets, and that space extended infinitely in all directions, filled with innumerable worlds. For this and other heresies, he was burned at the stake in 1600. Bruno's infinity was metaphysical, inspired by theology and intuition, not measurement. But he glimpsed something profound. That finitude might be a limitation of imagination, not of nature. It wasn't until the 20th century that we gained the tools to test infinity, not with philosophy, but with geometry and light. Einstein's general relativity, published in 1915, gave us the language, spacetime as a dynamic, bendable entity. But even Einstein, at first, believed the universe must be finite and unbounded like a sphere, because he thought an infinite universe would lead to gravitational paradoxes. So in 1917, he introduced the cosmological constant, not to explain acceleration, that came much later, but to hold the universe static and closed. Then in 1922, a Russian mathematician named Alexander Friedmann solved Einstein's equations without assuming a static universe, and found solutions that expanded, some finite, some infinite. Einstein initially dismissed them as suspicious, but just a few years later, Edwin Hubble observed that distant galaxies are receding, the universe is expanding. Einstein called the cosmological constant his greatest blunder, though, ironically, we now believe it's real and essential. In 1930, Howard Robertson and Arthur Walker formalized the idea of a homogeneous, isotropic universe, giving us the FLRW metric we spoke of earlier. And in the 1960s, the discovery of the cosmic microwave background confirmed the Big Bang and gave us a way to measure geometry. So the question of infinity moved from the realm of speculation into the domain of data. But even with data, ambiguity remains, because measurement always has limits. When Planck tells us the curvature parameter omega k is 0.000 plus or minus 0.005, that doesn't mean curvature is exactly zero. It means, if it's not zero, it's smaller than our ability to detect. And in science, we report what we can measure, not what we wish were true. That's why cosmologists say, the universe is consistent with flatness, not the universe is flat. Precision in language reflects humility in knowledge. Now let's consider quantum mechanics, because at the smallest scales, our classical picture of smooth, continuous spacetime may break down. In quantum theory, everything fluctuates. Empty space isn't empty. It's a seething foam of virtual particles popping in and out of existence, borrowing energy from the vacuum for fleeting moments, allowed by the uncertainty principle. The uncertainty principle, in words, says, the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a limitation of our instruments. It's a fundamental property of nature. Particles don't have definite positions and momenta at the same time. They exist as probability clouds, waves of possibility. Now, what happens when you apply quantum principles to spacetime itself? In the 1950s, John Wheeler proposed that at the Planck scale, about 10 to the minus 35 meters, spacetime might not be smooth. Instead, it could be a turbulent, frothy foam with tiny wormholes, quantum fluctuations in geometry, and even temporary changes in topology. He called it spacetime foam. In this picture, the very notion of distance, or duration, becomes fuzzy below the Planck length and Planck time. Asking whether the universe is infinite might be like asking how many drops are in a wave. The question assumes a level of continuity that doesn't exist at that scale. Loop quantum gravity, one approach to quantum gravity, suggests that space is made of discrete, quantized units, tiny loops or spin networks, and that the area of any surface and the volume of any region can only take certain discrete values. There is a smallest possible area, about the Planck length squared, and a smallest possible volume. If that's true, then the universe could be finite not because it wraps around, but because it contains a finite number of these fundamental quanta. Like a digital image, zoom in far enough and you see pixels. The image may look continuous, but it's made of countable elements. String theory offers another vision. Our three spatial dimensions could be a brane, short for membrane, floating in a higher dimensional bulk space. Other branes could exist nearby, parallel universes, separated not in our space, but in an extra dimension. Collisions between branes could even trigger big bangs, meaning our universe might be one cycle in an eternal sequence. In that framework, infinite could mean infinitely many branes or infinite extent along the brane or both. But again, we have no direct evidence for extra dimensions. Experiments at the Large Hadron Collider have searched for signs of them, like missing energy carried off by gravitons into the bulk, and found none, down to scales of about 10 to the minus 19 meters. So quantum gravity remains speculative, beautiful, mathematically rich, but untested. And until we have experimental access to the Planck scale, which may require a particle accelerator the size of the Milky Way, we won't know whether spacetime is fundamentally continuous or discrete. But here's a subtle point. Even if spacetime is discrete at the smallest scales, it can still approximate a smooth, infinite continuum at large scales, just as water looks continuous, even though it's made of molecules. So discreteness doesn't rule out infinity. It just redefines what infinite means: infinite number of quanta, rather than infinite extension of a continuum. Let's now return to topology and consider a thought experiment proposed by the cosmologist Jean-Pierre Luminet. Imagine the universe is shaped like a soccer ball, but not the surface, the solid interior. No, wait, better. Imagine it's shaped like a dodecahedron, a 12-sided platonic solid, with opposite faces glued together after a slight twist. This is called the Poincaré dodecahedral space, a finite, positively curved universe, like a three-sphere but with a more intricate topology. In such a universe, the CMB wouldn't show matching circles, because the topology doesn't produce circular correlations. Instead, it would suppress the largest scale fluctuations, the very biggest ripples, because they simply wouldn't fit. There's no room for a wave longer than the universe itself. And in 2003, Luminet and colleagues pointed out something intriguing. The WMAP satellite data showed a surprising lack of power in the largest angular scales of the CMB. Specifically, the quadrupole and octupole moments were weaker than expected in an infinite flat universe. Could this be a hint of a finite dodecahedral cosmos? The media called it the soccer ball universe. Excitement grew, but then Planck came along with higher resolution, better foreground removal, and the anomaly faded. It turned out to be partly a statistical fluke, partly contamination from our own galaxy. The large-scale power is now consistent with standard inflationary cosmology, no need for a soccer ball. Still, the episode teaches us something important. Science self-corrects. A tantalizing signal emerges. A hypothesis is proposed. Better data arrives. The hypothesis is tested, and if it doesn't hold, it's set aside. Not discarded in shame, but archived as a lesson, a reminder of how easy it is to see patterns in noise. That's why we require high statistical significance, 5 sigma, or a 1 in 3.5 million chance of being wrong before claiming a discovery. Because the human mind is wired to find meaning, even where there is none. Now let's talk about time, because infinity isn't just about space. Is time infinite? The Big Bang marks the beginning of our cosmic time, but was it the absolute beginning? General relativity predicts a singularity, a point of infinite density at t equals 0. But singularities are where the theory breaks down. They're not physical predictions. They're signs that we need a more complete theory, likely one that includes quantum gravity. Some models, like loop quantum cosmology, replace the Big Bang singularity with a big bounce. A previous contracting phase reached a minimum size, about the Planck volume, and then rebounded into expansion. In that picture, time extends infinitely into the past and possibly into the future. Other models, like eternal inflation, suggest that while our pocket universe began 13.8 billion years ago, the inflating multiverse has no beginning and no end. Time is infinite in both directions, but punctuated by local Big Bangs. Then there's the Hartle-Hawking no-boundary proposal, which says that asking what happened before the Big Bang is like asking what's north of the North Pole. In their model, time becomes space-like near the beginning. The universe has no boundary in time, just as the Earth has no edge at the pole. It's a closed, four-dimensional shape like a sphere, but in space-time. In that view, the universe is finite in space-time volume, but has no beginning point. It just is. So whether time is infinite depends entirely on the model, and we don't yet know which one is correct. But here's something quieter, more personal. Even if time is infinite in extent, your experience of time is finite and precious. Each breath, each heartbeat, is a localized ripple in the quantum fields that make up your body, a temporary, self-sustaining pattern in the cosmic flow. You are not separate from the universe. You are the universe experiencing itself, wondering about itself, falling through its own curved geometry. That's not poetry, it's physics. Let's now consider a different kind of infinity, not spatial or temporal, but informational. In an accelerating universe dominated by dark energy, the amount of information we can ever access is finite. The cosmic event horizon limits the number of degrees of freedom, the number of distinct quantum states that can influence us. In fact, using black hole thermodynamics, we can estimate that the maximum entropy, the maximum information content, of our observable universe is about 10 to the power of 122 bits. That's an unimaginably large number, but it's finite. And if the holographic principle is correct, which suggests that all the information within a volume of space can be encoded on its boundary, then the entire history of our causal patch could, in principle, be written on a two-dimensional surface surrounding us, like a cosmic hard drive. In that picture, infinity is not necessary, even for a rich, complex universe. Finiteness does not imply simplicity. A finite system can generate infinite variety, like a piano with 88 keys can play an uncountable number of melodies. So perhaps the deepest answer to, is the universe infinite? It doesn't need to be. But let's not stop there. Let's imagine for a moment that it is infinite. What would that imply for identity, for meaning? If the universe is infinite and roughly uniform, and if the laws of physics are the same everywhere, as all evidence suggests, then the number of possible arrangements of particles in a volume the size of our observable universe is finite. Why? Because quantum mechanics imposes limits. Particles have discrete energy levels, positions are constrained by the uncertainty principle, and the total energy in a region is finite. The number is staggeringly large, something like 10 to the power of 10 to the 118, a 1 followed by 10 to the 118 zeros, but it's still finite. Now divide an infinite universe into boxes, each the size of our observable universe, since there are infinitely many boxes, and only finitely many possible configurations per box. Every possible configuration must appear, not just once, but infinitely many times. So somewhere inconceivably far away, there is a box identical to ours down to the last photon. In it, there is a planet Earth, a city, a room, a person lying in bed listening to this very script word for word, breath for breath. And somewhere else, a box where everything is the same, except one quantum event went differently. A radioactive atom decayed a millisecond earlier, and that tiny change cascaded, altering a thought, a decision, a life. And somewhere else, a box where Earth never formed, or where life evolved into something unrecognizable, or where the laws of physics are slightly different if, as some multiverse theories suggest, fundamental constants vary from region to region. This is not fantasy. It's a logical consequence of three assumptions. 1. The universe is spatially infinite. 2. Matter is distributed more or less uniformly on large scales. 3. Quantum mechanics limits the number of distinct states in a finite volume. Drop any one of those and the conclusion fails. But if all three hold, and current cosmology suggests they do, then the infinite universe contains not just all that is, but all that could be within the bounds of physical law. That idea, called the Level 1 multiverse, is fully compatible with known physics. It doesn't require new dimensions, new forces, or new universes popping into existence. It's just infinity plus uniformity. But, and this is crucial, those other yous are not you. They are separate, causally disconnected entities. There is no communication, no shared consciousness, no transfer of experience. You are here. They are there, forever out of reach. So while the idea is mind-bending, it doesn't change your responsibility, your choices, your joy, or your grief. Your life remains uniquely yours because you are the one experiencing it. In fact, the existence of infinite copies might make this moment more precious, not less. Because even in an infinite cosmos, this instance of awareness, reading these words, feeling your breath, hearing the quiet hum of the world, is a rare and fleeting configuration. It will never happen again, not here, not now, not with this particular unfolding of cause and effect. So infinity doesn't diminish meaning, it frames it. Now, let's consider a counterargument, one raised by the philosopher Karl Popper and later by physicist George Ellis. If a theory predicts things that are in principle unobservable, like other Hubble volumes in an infinite universe, is it still science? Popper said that for a theory to be scientific, it must be falsifiable. There must be some observation that could, in principle, prove it wrong. But here's the nuance. The infinite universe model is falsifiable, just not completely. We could falsify it by detecting positive curvatures, say, omega k equals plus 0.02, which would imply a finite, closed universe, or by finding a repeating topology on observable scales, or by discovering that the cosmological principle fails, that the universe becomes radically inhomogeneous beyond our horizon. The fact that we can't observe the whole thing doesn't make the model unscientific. It makes it incomplete. All scientific models are incomplete. Newtonian gravity is incomplete. It fails near black holes, but it's still science. General relativity is incomplete. It doesn't include quantum effects, but it's still our best theory of gravity. Science progresses by building effective theories, models that work within a domain of validity. The infinite flat universe is an effective model, supported by data, predictive, and mathematically consistent. Whether it's the final word is another question. And that's okay. Let's now shift gears and talk about measuring distance in an expanding universe. Because how far is trickier than it seems. There are at least 4 ways astronomers define distance, and they all give different numbers for the same object. First, light travel distance. How long the light has been traveling times the speed of light. For the CMB, that's about 13.8 billion light years, because the light was emitted 13.8 billion years ago. But during that time, space expanded, so the object that emitted that light is now much farther away. That's the proper distance today, about 46 billion light years for the CMB. Then there's the comoving distance, which factors out the expansion, giving a distance that remains constant over time for objects moving with the Hubble flow. For the CMB, it's about 46 billion light years divided by the scale factor at emission, which was about 1/1100, so the comoving distance is roughly the same as the proper distance today. Finally, there's angular diameter distance, used when you know an object's true size and measure its apparent size on the sky. In a curved universe, this distance can behave strangely. Very distant objects can appear larger than closer ones, because light rays converge in positive curvature. This is called the turnover in the angular diameter distance relation, and it's another way we could detect curvature if it were strong enough. But again, in our universe, all these distances align with a flat, expanding model. No turnover, no anomalies, just smooth, predictable geometry as far as we can see. Now, let's talk about the future, because infinity isn't just about the past and present. If dark energy remains constant, if it truly is the cosmological constant, then the universe will expand forever at an accelerating rate. Galaxies beyond our local group will vanish from view. The cosmic microwave background will redshift into undetectability, its wavelength stretching longer than the observable universe. Star formation will cease in about 1 to 2 trillion years as gas is depleted or ejected. Black holes will dominate, slowly evaporating via Hawking radiation, a process that takes about 10 to the 67 years for a solar mass black hole. And in the far, far future, 10 to the 100 years or more, the universe will be cold, dark, and nearly empty. A thin sea of photons, neutrinos, electrons, and positrons, with black holes long gone. This is the heat death, not a fiery end, but a fading into equilibrium. In that scenario, even if the universe is infinite in space, it becomes functionally empty. No free energy, no gradients, no processes. Time may continue, but nothing happens. And if nothing happens, does time have meaning? Some physicists argue that time is defined by change, by entropy increase, by quantum transitions. No change, no time. So the end of time might not be a moment, it might be a state. But again, that's assuming dark energy is constant. If it decays, if the vacuum energy leaks away, then expansion could slow, stop, and reverse. A contracting phase could begin, galaxies blue shifting, temperatures rising, the CMB heating up. The universe would grow denser, hotter, until perhaps another bounce or a singularity. We don't know. What we do know is this: the universe has a history, and we are living in a remarkably special epoch. We exist after the first stars forged heavy elements, carbon, oxygen, iron. But before the stars have all burned out. We live in the cosmic noon, not the dawn, not the dusk. And because of that, we can look back and see the Big Bang's afterglow. Civilizations arising in the distant future won't have that luxury. To them, the universe will appear static, eternal, and small, and they may never discover its true origin. So our ability to ask, is the universe infinite? Is itself a fleeting opportunity? A window open for a few billion years in a 13.8 billion year story? That makes the question not just scientific, but urgent. Let's now circle back to curvature and consider how it relates to the total energy of the universe. In Newtonian gravity, A system can have positive, negative, or zero total energy. A planet in a bound orbit around a star has negative total energy. Kinetic plus potential is less than zero. It can't escape. An unbound comet has positive energy. It will fly away forever. In general relativity, defining total energy for the whole universe is tricky, because energy isn't globally conserved in an expanding spacetime. But in the FLRW model, there's a suggestive analogy. If the universe is closed, positive curvature, it behaves like a bound system. Expansion slows, stops, recollapses. Total energy, if we could define it, would be negative. If it's open, negative curvature, it expands forever like an unbound system. Positive energy. If it's flat, zero curvature, it's right at the critical density, the boundary between bound and unbound. And in that case, the positive energy of motion and matter is exactly canceled by the negative energy of gravity. In fact, some physicists, like Alan Guth, the father of inflation, have suggested that the total energy of the universe might be exactly zero. How? Because the positive mass energy of all particles, E equals mc squared, is balanced by the negative gravitational potential energy. Think of it like this. To assemble a planet from scattered dust, you have to remove energy. The dust falls inward, releasing heat and light. So the bound planet has less energy than the dispersed dust. Gravity is a negative energy store. Scale that up. If you could disassemble the entire universe, spread all matter infinitely far apart, you'd have to add energy. That means the current universe has less energy than that, possibly zero. A universe with zero total energy could, in principle, arise from nothing via a quantum fluctuation, without violating energy conservation, because zero equals zero. That's the idea behind the phrase, the universe is the ultimate free lunch. Of course, this is heuristic, not rigorous. We don't have a full quantum theory of gravity to make it precise, but it's a beautiful thought that infinity or finitude might stem from a perfect balance, a cosmic equation that sums to nothing. And yet here we are, breathing, listening, wondering. That's the miracle, not that the numbers add up, but that they do something. Let's end this part with a quiet reflection, one you can carry with you as you drift. Imagine you're holding a single grain of sand. Now imagine all the beaches on Earth, every coastline, every desert, every dune, and gather every grain. There are about 10 to the 18 grains, a quintillion. Now imagine a universe where every grain of sand is itself a beach, with its own quintillion grains. That's 10 to the 36. Do that again and again and again, 70 times. You're now at 10 to the 126, roughly the number of Planck volumes in the observable universe. But if the whole universe is infinite, then that number is just the tiniest fraction, an infinitesimal speck. And yet in that speck there is music, there is laughter, there is the smell of rain on dry earth. There is this moment where you, a temporary pattern of stardust, are asking one of the oldest questions of all. Is the universe infinite? We don't know. But the fact that we can ask and measure and wonder and lie here, falling through curved spacetime, is perhaps the most infinite thing of all. May your breathing slow, your thoughts soften, and your body sink gently into the support beneath you, not as something separate from the world, but as part of it, resting. You are not small in an infinite void. You are not lost in an uncaring cosmos. You are here, a quiet, conscious ripple in the unfolding of spacetime, held by gravity, warmed by starlight, made of atoms forged in ancient supernovae. The universe doesn't need to be infinite for your life to matter. It doesn't need to be finite for it to be whole. It simply is, and so are you. As you drift toward sleep, know this. Every question you carry, every wonder, every doubt, is a sign of something rare and beautiful. You are the universe awake, for now and curious. Let go. Let the curve of spacetime carry you. Let the silence hum its oldest song. Rest well. You are home. Good night.